Welcome everyone, day 3 of the Design Excellence Conference. So happy to have you. This session is called Reducing Embodied Carbon, Improving Design Decisions Through Life Cycle Assessment, with our speakers, Kate Sector and Roderick Bates. I want to thank our conference sponsors. Can't do this without them. They've been great supporters of the conference, especially Sierra Pacific Windows. And let's watch a very short video.
Sierra Pacific, windows that never compromise. Our mission, to do it right, to never compromise, to make the best windows and doors you can buy in the most sustainable way possible, from seed to delivered product.
Thank you so much, Sierra Pacific. Thanks to our speakers, and I'll hand it over to you now.
Awesome. Well, thank you all for being here. If you give me 1 second, I'm going to share my slides. Awesome. Well, thank you for joining us. We're going to be presenting on embodied carbon, reducing your impact through life cycle assessment today. And I'm here with Roderick Bates. Really quickly, just learning objectives for you. So the goal of this is that we are trying to educate everyone on embodied carbon and how to reduce your global warming reduction, or how to reduce global warming potential. And we're going to be doing this through looking at a few different tools today, primarily looking at Tally. And the main objective here is to learn how to measure carbon and effectively reduce it through different design decisions. And then I'll be presenting 3 different case studies that I've worked on so far at Lake Plato. So looking through the lens of the Design for Excellence framework, this is primarily focusing on designing for resources. And so designing for resources really around focuses on good design, really depends on informed material selection and balancing priorities between achieving design that is durable, safe, healthy, but yet most importantly, and what we're really trying to focus on, is reducing our environmental impact. And this is really critical when we look at the future of design, and that, we look at stats like this where we see that we're going to be building 230 million square meters, which is equivalent to a new New York City, every single month for the next 40 years. So we know that our impact is going to be substantial in the future. And so it's critical that we really begin to look at not only how that impacts operational energy, but our embodied energy and the materials it takes to create this. And so a building project causes environmental impacts far beyond its building site. And it's time that we start to pay attention to those impacts, whether that is acidification potential, eutrophication, ozone depletion, smog, even just human health and toxicity, and of course the impacts that we can visibly see on our environment. And the environmental impact that we're trying to focus on the most today is global warming potential. And this is also known as carbon or embodied carbon. But we are focusing so much on global warming potential because of its impact on climate change through natural greenhouse effects. And this is so important because of its adverse impacts on not just ecosystem health, but our human health as well. And one of the things that we are looking at as well is the fact that, from a global perspective, when you reduce CO2, you're also impacting some of those other impacts that we've mentioned, whether that's acidification or eutrophication, because global warming potential is one of those impacts that actually have an overall weight the most when we look at impacts overall. And so there are 2 ways that global warming potential is produced through the building sector. I think most of the time we think of that through operational energy, and which is why we've been so focused on trying to switch from fossil fuels to more renewables. But there's a whole other side to this, and the second way is through embodied carbon. And that really accounts for all the materials it takes to actually build and construct our buildings. And so we have to start to pay attention now to that impact, and the fact that, there's a whole other side to calculating materials impacts from the start, whether that's extraction all the way to the disposal of those materials. And Roderick will get more into that when we talk about life cycle assessment. And so buildings contribute a tremendous amount to our overall global CO2 emissions. I think a lot of you have probably seen this pie chart, but it still amazes me every single time I see it that, you know, there is a really big contributor when it comes to building operations, being 28%, but there's also a substantial amount that comes from just the building materials and construction itself. And this is going to just increase too as we begin to improve our building operations, and that we're really going to need to put our focus on that, you know, what seems like maybe a small percent right now, but is going to become even more impactful in the future. And so this graph essentially highlights that impact. And we can see, and kind of research has shown that between the next 30 years or so, embodied carbon is essentially going to be responsible for almost 49% of our global CO2 emissions. And this is even going to become more impactful and more important as our grid gets cleaner. So as we begin to switch towards operational energy that's on a much cleaner grid, that really puts our focus onto embodied carbon, which is why we're here talking about it today. And this is graphically another way that we can kind of display this really interesting phenomenon, is that when we look at, say, a typical building, you can see that primarily it looks like it's operational energy that is where we get most of our global warming potential from. And that leaves about a quarter of it to embodied carbon. But then as buildings become more high performing and our operational energy decreases, right, that focus, like we're saying, becomes more 50-50, which is why we really want to start paying attention to it. But then, of course, as your building becomes net zero and you don't have any impact regarding operational and global warming potential, the big focus really does become embodied carbon, which I think is really exciting to say that we're on this really positive track, but now we need to put just as much effort and focus into embodied carbon as well. And so carbon emissions, unfortunately, they're continuing to peaking, and we know that we have to start reducing it now. It's very clear that we have a carbon budget that's available, and we can't go past that 1.5 degrees Celsius impact. And this isn't just the buildings in general, but this refers to the built environment as a whole. And it's been kind of clear that we have some goals set in place, such as achieving 65% reduction by 2030 and hopefully phasing out by 2040. And this is really critical because there's a lot of research done by the IPCC and the UN and other scientists that are showing that this is kind of a critical threshold that we need to address in order to make sure that we can kind of move away from the negative impacts of climate change. And so, you know, this essentially is an immediate call, right, for embodied carbon as well to begin reducing. And I don't know if anyone else finds that really daunting and is slightly overwhelming, but I think this slide is what gets me really excited about embodied carbon, and Roderick shared this with me, but it really just goes to show that this is possible. We have steps that we can take to start reducing not only operational, but now embodied carbon. And I think that's a really hopeful path. And so a lot of it really comes down to starting early, making sure that we're addressing embodied carbon right from the start in early SD. There's a lot of things that we can do to help kind of slowly move down the path towards zero, whether that's reducing your cement content in concrete or reducing steel, and we're going to talk more about these impacts, but selecting bio-based materials that help with sequestration and reducing that kind of impact and reversing it. There's also strategies for optimization, whether that's in foundation or your steel content. Using reclaimed materials and retrofitting is a huge way that you can help reduce your embodied carbon, as well as then just being net zero in operations. And then there's also, of course, carbon offsets, which is another way that you can begin to offset, say, the materials that you can't reduce substantially. And so I'm going to hand this off to Roderick now. Thank you.
Okay, so I think, oh, wow, that's a big problem. How are, what's the means by which we can actually address and resolve this challenge of carbon and get to that ideal zero figure for embodied carbon? And unfortunately, this isn't a new problem, and there's been methodologies developed out there to address and to quantify those impacts. Because frankly, if you don't quantify them, you can't begin the process of reduction. So the methodology for doing that, of course, is life cycle assessment. And what this means is that you're essentially evaluating all the things that go into making a material during that point of manufacturing. So that's the idea of the resource extraction, maybe the cutting down of trees, the mining of ore, the collection of scrap material for inputs and things like that. Then all of the energy, other chemicals, things like that that go into the manufacturing process. And as those things go into that process, of course, there's pollutants coming out of them, among which, of course, is greenhouse gases. And then after the manufacturing, everything has to get to the construction site. You have some impacts associated with construction itself. During the occupancy of a building, there's actually a fair number of impacts that happen as materials are, say, replaced, repaired, things like that over, say, the 60 or 75 years that a building's around. And then at the end of that building life, you have the demolition and recovery process, when some of those materials are extracted, back out, disposed of in various ways, and then recycled and whatnot, and hopefully re-enter the stream. So at each one of these processes that you have, each one of these stages, there's going to be impacts that are going to be incurred. So when you look at this through the lens of life cycle assessment, all of those different processes get broken down into what is referred to as modules. Those modules are the manufacturing, construction, use, end of life, and then module D, which is sort of a separate unit off to the side that deals with the recovery of materials themselves in their reuse. And so at each one of these stages, you can see here, you have this inputs of materials, energy, and water. And then out of that, you're going to have emissions. And there's a lot of different ways in which you can slice the life cycle assessment. From the perspective that most people think about this, it's really what they call a cradle to grave, meaning you're looking at a material from its inception of raw materials in a manufacturing process, all the way through the complete building life, demolition, and then recovery. But it's also possible to look at these impacts from what they refer to as cradle to gate. And that's just the manufacturing of those materials. It's kind of like what happens in the factory itself and how those materials get to the factory. And then it stops at the factory gate. And then there's also gate to gate, where you're looking at what happens when something leaves the factory, gets to the site, and then you're stopping at the site and not looking what happens when something leaves the site itself. So you're ignoring that end of life. For the purposes of LEED and things like that, it's always cradle to grave. And when you're looking at an EPD or an environmental product declaration, which is typically a product specific life cycle assessment, is typically a cradle to gate, although some of them do include cradle to grave, but typically it's cradle to gate. So you want to perform an LCA, or you want to reduce the impact of your building. Well, LCA is essentially a tool, and you have to find the right ways to apply that tool. So how do you know when the situation is correct? Well, the first thing is that LCA really works well as a comparison. Is option A better or worse than option B? And when you have those types of situations, it's very easy to use LCA to make, or at least help decision making. And of course, in both those contexts, it relates to design decision making. So in a sense, that's the point here. You're trying to help facilitate making a decision. You're not just trying to find out something interesting, but actually using the information that's generated. And then the question itself you're asking implies what's referred to information about a functional unit. And I'll detail what a functional unit means in a second, but just to put that briefly, what it means is that the information is specific to a particular application. And that application is consistent amongst the options that you're comparing. And then last thing is that the option or the question is one that actually matters with regards to the materials you're selecting. So it helps you, say, choose between options that are not only about materials, but also perhaps about dimensions, structure, and things like that. So what does this LCA look like as a process? Let's describe the components of the tool. The first thing is that it's a process. You want to start with defining a goal and a scope. So you actually have to know what you're doing before you get started. Then the second piece is collecting inventory. That's understanding how much stuff you have, all these materials, actually what's the quantity of them, theoretically. And then you actually have to assess the impact. And then you're going to get results from that. And then you want to analyze those results and then probably feed back into a process where you once again create a new question and define a goal and scope. So what does that mean with this goal and scope definition? Well, it really revolves around this core concept of functional unit. So with the context of a functional unit, you actually have a quantity of something and a performance attribute associated with it. So if I were to get my cup, the performance of this cup is to hold water and allow me to sip this water and then be able to clean it and reuse it. It's the same thing with a piece of a building material. Say you have a 2x4, it has to function in the context of building framing, last the life of the building, things like that. The great thing about a functional unit is that you can have very different materials performing the same function. For instance, you can have a wood structure, you can have a concrete structure. They're both performing the same function over the same area of a building. So they have those same performance attributes, but are obviously vastly different materials. So once you've defined the goal and the scope and that functional unit that you want to achieve, your next thing you need to do is define the quantities of materials that are relevant to that functional unit. In this case, you're looking at a whole house. So the functional unit would have been an entire house for a family of, say, 4 over 65 or 75, what have you, years. And this is all the pieces that went into that particular house. So from there, you would say, okay, now I know all the pieces. I've done my inventory. I know all the little bits and pieces of my building. The next thing you want to do is you want to sort of multiply, if you will, the impact of each one of those materials against that total quantity. So as an example of this, let's say you have 100 kilos of steel in your building, and you know that each kilo of steel has an equivalent embodied carbon of 0.43 kilograms, and you're going to have 43 kilograms of global warming potential in that particular building. There's a lot of great tools out there to perform this particular calculation. Some of them are particularly good at perhaps creating the inventory. Some are less good at that, but are very good at quantifying the impacts if you happen to know your inventory. But all of them will create a total impact figure that can be used to leverage design decision making. And just as a note, on the bottom, there are some of the 3 more popular tools, Athena, One-Click LCA, and Tally. And I would definitely say that all of them have their place and they're all quite effective. Okay, so now you're looking at the impacts themselves. You've created your inventory, you've used the software to create an inventory of impacts. So what are those impacts themselves? What do the results look like? Well, the results are organized into what is called a categorization scheme. And in the US, we use a categorization scheme created by the US EPA called TRACY, and specifically TRACY 2.1. TRACY 2.1 reports figures along these lines, what they call global warming potential, which obviously is fairly familiar, and it's the primary topic of this conversation, which is the impact associated with the greenhouse gases that are emitted. But there's also other impacts, acidification. Obviously, acidification is a familiar topic to people in the context of acid rain, but this is a situation in which you basically increase the acidity both in the soil and in the water, impact crops, impact flora, fauna, can be quite severe. Eutrophication, this is where you have a large nutrient, say nitrogen and phosphorus input, particularly to water bodies. So if you're, say, down in some of those Gulf states and you see these large algae blooms, that's a result of eutrophication. Then you have ozone depletion. This is when you have the emitting of chemicals that go into the atmosphere and result in depletion of the ozone layer. Fortunately, this as an impact is actually incredibly small now, as a testament to the success of the global initiative to curtail the use of CFCs and other ozone depleting chemicals. So if everyone ever says that there's no hope in all of this, I think that the dramatic decrease in ozone depletion of materials is certainly testament that that's not the case. Smog formation, so this is all of those direct particulate emissions, sulfur dioxide, things like that, that are emitted in the course of manufacturing, direct impact on human health, exacerbates people with asthma, breathing problems, things like that. And then you have energy demand. This is the primary energy demand, both renewable and non-renewable, that goes into manufacturing those materials, say processing them during the waste phase and things like that. It should be noted that during each one of these phases, you're not only going to have things that are emitted, but you're also going to have things that actually reduce the impact associated with each one of these categories. So you're going to have sort of, you're going to have pollutants and you're going to have credits. And these will all get totaled out by the tool. The other thing to note too is that within each one of these categories, there's a wide variety of different types of pollutants that can be contributing, but they're all just lumped together into acidification, global warming, eutrophication. The reason they do this is you don't want to break out each type of chemical. Let's say in the case of global warming, you might have very severe methane emissions during end of life for wood as it decomposes and goes into the atmosphere. But at the same time, you might also have, say, combustion of that wood where you're going to be emitting carbon monoxide, carbon dioxide. They're going to aggregate both of those impacts into global warming potential. So the idea is that each one of these serves as these buckets in which you put pollutants that impact this particular category of environmental performance. So that's LCA in a nutshell. But what does it look like when you're applying this to a project itself? What is that particular workflow? Well, I've been at this game for a while, and I can say that the typical workflow was one in which perhaps it's not so typical anymore, but it was when we first started performing life cycle assessments. And essentially, life cycle assessment, because of the complexity of the process and the challenge with quantifying all those materials in your building and understanding all the impacts, ended up being done once at the end of design. And when you did that, you realized all the terrible decisions you made, and hopefully a few good ones, but there was really nothing you could do about it to improve your design. So having done this a few times, we realized that there's a real need to be able to have this information, this life cycle impact information of various material options in real time. If you're making a decision about materials, you need to have the life cycle impact information at that time. So what we wanted to do is create a process that looked like what you see on the bottom. We refer to that as a Tally workflow. This is what we set out to create when we created a software called Tally that's being used by a number of entities around the country and in fact around the world to perform life cycle assessments on their architectural projects. So the Tally software came about because of a need, obviously, but it also came about through a partnership between several entities. One of them is KT Innovations, which is a subsidiary of the architecture firm I work for, which is Kieran Timberlake, sort of our division that sort of spins off some of the interesting ideas and capabilities we have to allow for greater public use. We also partnered with a company that specializes in LCA data. So we talk about global warming potential of, say, a kilogram of steel. I have no idea where to get that number. But fortunately, ThinkStep, Sphere company, that is what they do. They perform those types of life cycle assessments for a variety of industries, from automotive manufacturing to high technology, all sorts of things. And in the process of that, they've created a very large database of material impacts. And then we also worked with Autodesk so that we can integrate our software directly into their Revit modeling platform. So the idea being is that the same people that are modeling in Revit are the same ones that are using Tally and making life cycle assessment decisions. And you can see what that looks like in this diagram here, where you have the Revit model, and then Tally from that Revit model creates a initial bill of materials that then through the Tally interface is refined and made extremely accurate. Then you combine that bill of materials with a database of impacts that come from ThinkStep. And then at the end result, you get a highly legible Tally output report. So what is the crux of the challenge, at least as we see it, in performing a life cycle assessment? I mean, it's an easy concept, right? How much stuff do you have? What's the impact of the stuff? And then you get your final figure. The challenge is that figuring out how much stuff you have is not so easy. A Revit model is designed for the purpose of basically design or constructing a building. It's not there to create a line item inventory of every little piece that you have in your building. You're not quantifying your grout or your tiebacks and things like that in your Revit model. So what we had to do was create a mechanism through Tally in which people could design in Revit as they normally do, not changing that, but rather instead have the mechanism through the Tally interface to be able to input the additional metadata that enables the creation of that accurate bill of materials. So this gives you a brief example of what that looks like. And by virtue of being architects ourselves, just to be clear, I'm not an architect. I'm probably more a problem creator than anything else, and maybe an occasional solver, but we do work in the context of an architecture firm. And so we understand how Revit is used for design authorship. So the idea being here is that we are creating a mechanism by which we sort of query the user as they go through their BIM model in the Tally interface to input additional metadata. So you can see this example with brick, where we'll query them for, say, the mortar type, the grout, if there is any reinforcement that would be there, the finish, all those things would otherwise not be modeled when you throw a brick into a Revit model. So what does this look like potentially in practice? And what does this look like at different phases of design? So obviously you're going to want to, if you are really doing iterative LCAs, do it throughout the design process, from early phase to later phases. We're actually comparing options to the end of project benchmarking. So early phase, sometimes it's very important, even if you have a very coarse model, just to do an overall assessment. And we do this, what we call sort of contribution assessment. So you can understand essentially where your big impacts are and where the opportunities are for reduction. So in this case, this is an actual project where we did a very early phase life cycle assessment. And we found, interestingly enough, that finishes were a big impact. And as we started to dive in, we found out that it was a fluoropolymer coating on the exterior envelope. The other thing that we found, of course, no surprise, is that concrete is a biggie. So this told us two things. One is, okay, let's look at our finishes in this project and see what we can do to reduce the quantity or switch the type of finish. And then alternatively, or additionally rather, look into our concrete mixes and see what opportunities there are to reduce the impact there. So just as an example in the context here of concrete, and in Tally, it's fairly easy to create a comparison of various concrete types. So in this case, we just created a functional unit of structure, not necessarily the whole structure, just a functional unit, maybe one structural bay, and then switched out in the concrete types to look at different percentages of fly ash and to see what the associated reduction would be. One of our users, the Tally user, ZGF, created an even easier way of doing this. They essentially hacked our software and created a mechanism via spreadsheet where you can very rapidly propose different mix designs and compare them to NRMCA baseline mixes for your region. After they did this, they reached out to us and said, hey, can we make this public? We thought that was a fantastic idea. So you can search this on the internet. I think it's, was it LCA tool at ZGF. And they will actually, if you email them, send you a copy of the spreadsheet. But it uses Tally data, so you know it's good. But also it's a really easy way of comparing concrete with a free tool. So maybe you've done those big decisions and now you're getting a little bit more into nuanced design and you want to compare some actual options. In this case, the functional unit that we're looking at is a lower portion of a wall on a building, one that's brick and one that's concrete. And how do these two compare against each other, say looking over 100 square feet or something like that of this particular assembly? And you can see when we look at these that the dramatic difference in impact. And it really sets up a very effective comparison. And obviously there's a lot of other factors at play, but this is one in which you say, okay, if you're trying to prioritize global warming reduction, clearly we want to look at the brick option in this case. And then as I showed earlier, finishes were a big impact on this particular project. So you can see some of those variation in finishes that we have with various materials, and the finishes here shown in red. So depending upon what type of finish we chose, you can see the fluoropolymer is actually not terrible relative to some of the other options, but finishes still are significant despite the fact that they actually occupy a minuscule amount of the overall mass in a building. So what does it mean though when you've used Tally throughout the design process? What does that mean when it comes to actually building something that achieves that intended performance? And this is one of the gaps that we've always been concerned about. Maybe you've chosen the great options and assembly types and things like that, but how does it get reconciled with what you actually end up getting built, building that's on the ground. And we ended up partnering or developing an integration for rather EC3, or the Embodied Carbon Calculator, that was developed by Building Transparency. And this is a fantastic tool where it allows for Tally users to export a bill of materials from Tally into EC3. And once that bill of materials is in EC3, you can match that bill of materials against specific products that have EPDs, or environmental product declarations. And those EPDs, while they only include manufacturing impacts, allow for you to select within a particular category, say concrete, or maybe you're looking at your carpet options, select the best performing options, and then tie those into your procurement specifications and purchasing process. So that what actually gets built essentially realizes the performance that was intended in your Tally analysis. So this is an example of that EPD that you would have. Obviously, these EPDs don't include things like maintenance, replacement, loss in times. They don't include end of life or module D. But since you've already assessed that from a sort of assembly and generic comparison within the context of Tally, comparing the specific manufacturing impacts of like materials within EC3 is a very effective way of really achieving the best possible performance from your built project. The last piece of all this, of course, is benchmarking. And how does your project actually stack up? Now, there's a couple of things to note here. One is that there is no national benchmark yet. So this is a screen capture of our own internal benchmarking software that we use internally, that we developed. And you can see that there's a huge variation and things are getting better, thank goodness. But fortunately, the AIA with its DDX exchange is going to include embodied carbon starting in October. We're really excited about this. It's going to be a mechanism that allows for a variety of tools to input data into the user's DDX account for their specific products or projects. And Tally will have an integration to allow for that as well. So we're very excited. Keep an eye out for that in October, but that does mean that when you perform a embodied carbon assessment for your project, you'll be able to compare it against other projects that are out there within the same category and region to understand your relative performance. So one of the key things we realize as a tool developer, particularly for a process like LCA, which is sort of on the upswing of adoption, is that providing educational resources is incredibly important. So one of those is LEED. We provide a LEED guide that explains things like baseline buildings. What does that look like? What sort of documentation is required? What's in scope? What's out of scope for the purpose of LEED? We have a number of other fantastic resources, including webinars that cover topics ranging from, say, biogenic carbon to reducing the impact of steel or concrete in your building. A lot of these are tool agnostic, not specific to Tally, but really on the topic of LCA in general. So definitely check those out at choosetally.com. And last thing is that I want to talk a little bit about what the process of lifecycle assessment looks like at our firm. And one of the key things is that we do is underbalance this idea of environmental impact, cost, and the user experience. And that LCA is just one of a variety of factors that gets put into play when it comes down to design process, decision-making. So for us, part of that process is that at design kickoff, we really identify LCA goals. We have to have a goal. I'm on a project right now where the goal is true net zero carbon for operations and embodied impact by the end of that building's life. So that's the goal. We'll see if we can achieve it. I think we will. During design, one of the key things is you actually have to integrate your LCA tools into your workflow, and that you're able to do LCAs at various stages to check overall performance. And then during construction and completion, it's all about benchmarking, understanding your performance, communicating that to the team, and ideally communicating it to the general public as well. So with that, I will hand it back to Kate to talk about her process at Lake Flato. Don't forget to unmute yourself too, Kate.
Saw that. Yes, sorry, realized my slide deck restarted. Okay, awesome. Thanks, Roderick. That was really great. I'm going to finish up by talking about some case studies that we've been working here at Lake Plato. And, I just also want to say thank you again to Roderick, because a lot of the reason that I've gotten really involved in this is because of his responsiveness and ability to work with us, and just all the great resources that have come out of Tally and even the Carbon Leadership Forum. It's been really inspiring. This started just as research and development for us, and it's now something that we're also trying to really integrate into our work, because, at Lake Plato, our ethos is around sustainability and connecting with nature and providing place-based design. And a big part of that, comes with biophilia and aesthetics, but it's also coming down to now, how do we actually influence, the built environment through data and research? And that's why, we've really made it a big part of what we're doing now, is looking into embodied carbon to help us improve our design decisions. And, kind of connecting back to Roderick's workflow, this is something that we're in the process of going through right now, is creating a workflow that works for us and uses Tally and some of the different tools that we're integrating. We're trying to make sure that we have a really good method for figuring out what our goal and scope is, especially that functional unit that Roderick was talking about, making sure we have a solid template. We're working through different BIM standards right now to highlight whether or not we're going to be doing a whole building LCA or design options, and also just how to perform those assessments in a process. There are a lot of different tools out there, so we're all trying to just explore right now what works best for us. And also coming up with request forms, because like Roderick was saying, that the specification part of this is really important, and that's something that we have to get better at, requesting EPDs and making sure that's integrated, so that all the hard work we do in the beginning actually comes to fruition. So I'm going to walk through 3 different case studies. And this first one here, or I guess I want to say that each of these tries to kind of bring home a main point, to highlight all the different ways that you can use an LCA tool. There's so many different ways. These are only just a few that we've done so far. Fortunately, a lot of these were done, when Roderick showed that overall workflow done at the end. But, we're really trying to focus on ways that we can actually begin to integrate this into our workflow. But this project is really exciting because it tells a story of how important retrofitting is and reusing materials to start. And so this is a project here in San Antonio. It's Pro 21 Broadway Lofts. And what's really exciting about this story is that this was an abandoned kind of building shell. It was highly vandalized in this area. And so Lake Plato took on this project and turned it into something really beautiful and amazing. But the important story behind this, right, is how much carbon was saved by reusing this structure. This is a 5-story complex on 5 acres, so it's quite substantial. And we were really curious to learn more about how much we actually saved and how big of an impact that might have had on the environment by reusing this structure. And so using Tally, I basically only looked at the primary structure, which was just structural concrete and some CMU block, which is that little icon there on the left. And through using Tally, we found out that we essentially saved roughly 12 million kilograms of CO2 equivalent. And so this number might be hard to comprehend. So you could also say that we essentially took off 9,500 passenger vehicles off the road for a year. So that's about what equates to 12 million kilograms of CO2. Another way to look at this, so this map is to scale, but we could have also said that if we had to have built this structure again, we would have had to essentially create 950 acres of forest and let that grow for 60 years to sequester all of that carbon that would have been produced in the life cycle of these materials. So it's quite an amazing story of just how important it is to reuse what you have and how much of an impact that can have on the environment. And, take this a little bit further, we also wanted to kind of bring back the idea of what is the trade-off when it comes to retrofitting, because of course you can't always do that, and sometimes retrofit isn't really the best option. And so this graphic is highlighting two scenarios. One is a retrofit building that has a worst and best case scenario for UI or operational energy use intensity. And so you can see that we theoretically said, well, if we retrofitted this building, we're saving 12 million kilograms of CO2. But at what point is that not worth it? Because then you have to consider your operational energy. And so say if this had been a really efficient building, then of course it's worth it. But at some point, if you were to retrofit but not create a higher efficient building, well, then maybe rebuilding the structure and having a lower EUI or more efficient building actually might have been worth it in the long run. So that's just something that we're always trying to keep in mind, is that although we're talking about embodied carbon today, right, operational is still at the top of our mind, and it comes at balancing the two best options. So the other case study we did, this was a whole building LCA. And so this was, the main purpose was getting some extra LEED credits for our University of Denver Career Achievement Center in Colorado. And this was the first time that we had done a whole building LCA. So it was a really interesting process to go through, and Roderick again helped us with this. So it was really awesome to get his expertise here. But so we found out that there's actually quite a lot of points that you can get when it comes to LEED and this option 4 of whole building life cycle assessment. And so what's interesting about the LEED credit is that it looks at all impact categories. It's not just global warming potential like we've been primarily talking about today, but you have to take into consider everything and equally reduce it as much as you can. And although it's called, a whole building LCA, it's primarily focused on structure and enclosure and foundation. So it doesn't quite include, the MEP and the site and everything around it. And I guess, to tie back in the importance of defining your goal and scope too, this is where LEED has a very clear goal and scope, right, of this required components that you're analyzing, as well as what impact categories that you want to look at. And so a big component and lesson learned from this project was understanding how to create a baseline. This is the first time, I had experienced this, and really LEED just describes baseline as something of comparable size, function, orientation, operating energy, and service life, right? So it's a bit vague, and given that there isn't baselines right now, like Roderick was saying, right, we have UI baselines, but we don't quite have a baseline for when it comes to carbon. We had to get pretty creative when it came to, what is our baseline worst case scenario building? And so that was a whole process in itself of essentially copying this model, changing a bunch of materials, and rerunning Tally on it to show how we are actually improving through our new building design. And so this is essentially the inputs versus the results that we got. And so this Denver Career Achievement Center, it had a lot of really great material use in here. We were using a lot of local glulam in order to help offset some of that carbon. And this was one of the first timber buildings in Colorado, or the kind of big mass timber buildings. So it was a really exciting project, and we wanted to really celebrate and show the research on how much we improved our environmental impact by making those. And so this is where, we essentially created a baseline building saying, well, worst case scenario would be that instead of using glulam column and beams, we would have been using concrete or steel. And then we also changed some of our exterior facade materials, some of the roofs and membranes, the flooring, we slightly adjusted everything to make a worst case scenario to benchmark against. And found out that, we had quite a substantial reduction compared to this baseline. And although we didn't get the full 5 points, we got 3, which I thought was really exciting. So the 3 points that we received for this project was because we reached a minimum of 10% reduction for at least 3 of the impact categories. And then you can't increase any of your categories by 5%. So I think just when it comes to LEED, even if you were to just run the analysis, you would still get 1 point. So I think doing this process, it's really nice that LEED is encouraging this and making it part of their credit library. So yeah, just to reiterate, there was a lot of great lessons learned just from even trying out a whole building LCA for the first time. A lot of that was just establishing a baseline and what was required, how important it is to use biomaterials, and the glulam beams and timber that we used were really important in helping sequester some of that carbon that the other materials were producing. There was some interesting challenges in the end when it came to trying to balance the different materials, because one of the things we noticed was that the more timber we included, sometimes that ends up raising your eutrophication potential. So although you might make one big design move, there also has to be a balance, and sometimes that's why it's really important to do a whole building LCA and look at it much more holistically. And then a lot of the other kind of ideas of reducing concrete and specifically cement, and also optimizing steel. Even though maybe we can't fully emit those products, there are ways that we can more strategically implement them. And I'm going to talk through our third case study a bit more on what some of those strategies are. Right, so this is the last case study. This is Gulf State Park Lodge in Alabama. And so again, this was one of those kind of more theoretical studies that we did after the project was built, because I think ideally we would have loved to use a lot more timber in this project. But we wanted to see, in the future, if we could implement less carbon intensive products, what would that look like? And what would that impact be, and some of the future lessons learned from this. And so this was one of the ones we put some extra research in, of trying to understand if we could have made one big move to improve the embodied carbon of this building, what would it be? And so this was a graphic that I saw at Greenbuild and I thought was really interesting, because it highlights how much CO2 comes from just the structure alone. And if we could maybe focus on one building component, structure is a really great place to start. Of course, interiors and a lot of other things play a big role in this, but we ended up saying for this kind of theoretical project, we want to go ahead and focus on structure. And so this is also a really kind of interesting graphic to show from the original one that we were looking at, where this highlights more what materials are actually causing this CO2 emissions within the architecture field, but this is now within the kind of built environment and all industries in general. And we see that the primary causes of CO2 production are from concrete, steel, and aluminum. And it's quite a significant percentage if you look at this as a whole global impact. And so, when we're trying to answer the questions of, well, what materials should we be using for our structure, this research helped us kind of put more of our focus onto timber. And you can see kind of in this right diagram here that concrete and steel have quite a large margin of error, but it tends to be significantly higher than, say, timber. But that also goes to show that concrete and steel can be used efficiently and have a lower embodied carbon impact if you're really careful about what you're speccing and including. And so we decided to do a bit more research into timber and how to use it responsibly, because you can kind of see in this graphic, the top is showing that timber is essentially always going to be better than a concrete design. But you can use timber in ineffective ways, which is why we have to be really careful that you can't just automatically put timber as your best case scenario. And so, because with a timber design, you could have really worst case scenario sourcing and transport, which makes it not as effective and doesn't really reap the benefits of sequestering. But of course, timber is quite an amazing material because it does have that sequestration ability. And so when your basically best case scenario for this is the kind of shorter transport distance and using sustainable forestry practices, which is really a key component of this. And so some of the kind of tips or things that we learned from this process is that the certified forests are really important to use. So FSC, if you really want to reap the benefits of that. Also, when you're using LCA tools like Tally, making sure that you're selecting the biogenic carbon box is really important because that is what gives you the sequestration ability, or it includes it in the data. And yeah, and some of the other tips are mostly just integrating it early and working with MEP and code compliance. So then, we can't always reduce or completely omit concrete and steel from our design, but how do we at least reduce our embodied carbon for the materials that we do have to use? And so some of the things that we learned from this process was that primarily 6 to 8% of global CO2 emissions within concrete is just from cement, which is why it's really important that we're trying to use less Portland cement right now and find different ways to supplement that, whether that's through fly ash or other content that's coming available. And also only speccing strength when you need it, so making sure we're not over speccing and having just essentially what is essential. Another really interesting way to reduce the impact of concrete is also through carbon injection or products such as carbon cure. And I definitely recommend looking into this. It's really interesting as a method of reducing cement and an alternative method of injecting carbon. And that's been a really creative and innovative way recently to get into this. And then of course, just reducing waste where you can when it comes to concrete is another way. And then when it comes to steel, some of the things is of course using recycled steel. Fortunately, this is something that happens in the industry already, which is really great to hear that we can use recycled steel as much as possible. Another interesting way to do this is researching the type of furnace that's being used in the manufacture. So you can look into how clean or dirty that energy used at the facility is in order to help improve that embodied carbon emission. And then of course, there's also steel optimization. People are getting really creative in ways to optimize their building to reduce the material needed, but still have the same structural support. Okay, so getting back to our design after doing all this research into it, we came down to essentially doing a very similar process in Tally where we copied our model and ran a different scenario on it using different materials. So we decided to go through this design using primarily CLT. And so we wanted to compare if you had your traditional building of concrete and steel, how would that compare to using CLT instead? And this is just within the structure. And the results that we got were really interesting. We found that, when we're including biogenics, so that sequestration ability of the CLT, we reduced our embodied carbon or global warming potential impact by almost 52%, which is really exciting to see that when you are using timber, it can significantly drop your CO2 production. And this also, I included the excluding biogenic option because this really goes to show that it's important to check that biogenic box because that is how you really reap the benefit of that sequestration ability, or else you won't quite see that same significant impact. Yeah. And another thing that we really were looking into is how to actually talk to clients about timber and to show them that beyond just the environmental impact, there's a lot of benefits to using timber products in their building. One of the things is just that it's really innovative and exciting right now. We're seeing a lot of codes start to actually comply with and allow us to build larger buildings and become, we just have a lot more exciting options when it comes to timber now. We've also seen that you can lease these buildings at a much higher rate. So for developers, this is really exciting. And there's also a chance that it's a higher speed of construction, and the construction itself is a lot quieter. And this is also because it requires less labor-intensive processes. And then in the long run, we've also seen that it can save money too, although timber is a raw component that might be more expensive upfront. In the long run, when you consider construction costs and just the overall process, we've seen that it's actually can save money in the end in some scenarios. And then most importantly, it's just a beautiful product and it's healthy. And I think, we've seen all these images today that timber is a really exciting product to be using. And so I just want to end with a slide that I really liked from Ed Mezzaria's talk at Architecture 2030. And it really goes to show that throughout history, we've had all these tools and we've accomplished so much with what seems like very little tools today. And I think it just goes to show that we can accomplish so much given what we have now. You know, we have all these really great tools like OneClick, Tally, the Carbon Leadership Forum as an organization, Cove tool. You know, we can accomplish so much. And I think that although it sometimes seems like a very daunting task, we can do it. You know, we have this ability given the tools we have today, which I believe is really promising and exciting. And I guess just to end that, you know, it is our responsibility, I think, as designers, architects, engineers, everyone in the AEC industry, that we're aware of these impacts and we have the tools to do it. And it is our responsibility to begin to research this and find ways to integrate it into our overall workflow. That is all. Just want to thank you for having us. I think we have time for Q&A, maybe 5 minutes, but we'd love to answer some questions for you all.
Okay, maybe I should take the first one because I had mentioned this idea of a true net zero project. This is a question from the audience here. On that particular project, you know, I personally don't like the idea of purchasing offsets, although it certainly can be done. In that particular project, it's challenging because it's a clean grid. It's actually a hydro grid, but it does have peaker plants that make up sort of the marginal demand when the hydropower can't suffice. And so what we do is we have on-site solar, and we're right now running a calculation to determine through battery storage on site when we could basically put power back onto the grid when it's using the peaker plants, and count that as an offset for the building itself. Otherwise, the building is able to use its PVs for the rest of the power demand. And we're also able to get the embodied carbon figure exceedingly low because it's a residential structure, primarily wood. But right now we're tackling the issue of foundation and how we can reduce the impact of that. Obviously, residentially, you can't do some really cool concrete mix, but we're looking into ways in which we can essentially minimize the amount of concrete with alternative structures and filling, things like that. So success hasn't been achieved yet, but we're on the right path. And it looks like we have another one. The use of timber reduces environment's ability to, so what about the concern that the use of timber reduces the environment's ability to absorb existing CO2? First of all, I would say if anyone's interested in timber, I would definitely recommend you go to the Carbon Leadership Forum and find in their webinar recordings the 8-part series, I think it was, on wood. It is without a doubt the definitive subject of wood. But the real thing is when it comes to biogenic carbon is that you replant what you've cut down. And that's a core part of FSC, and that's the reason why the performance is so great. And it's typically part of harvest or timber practices in the United States, Canada, but not everywhere, to be perfectly honest. So it's definitely one of those places where source matters, FSC certainly matters, and if you can afford that premium, go for it. Maybe you should talk a little bit about, Kate, you're in Lake Flato. Do you run an LCA, or do you have plans to run an LCA on every project that comes through your doors?
That's a really great question. I think ideally we would love to. I think we're still in the process right now, like I shared with our workflow, of trying to understand what is possible to do that. It does take some time. I do run the LCAs in the office right now, and I think part of what we're trying to do is to train our staff to also just show that everyone can do this. You know, it's not limited to, say, myself, who's more of an environmental consultant in the firm, but we really want to encourage all the designers to use this tool because they can.
Absolutely. They're the ones picking the materials after all, right? So
exactly. So it's really important that we get everyone doing this, and that's something, you know, we're working on a design performance action plan right now. And I think part of our goal is going to be to use LCAs as much as we possibly can because it's absolutely essential right now.
And just to speak from the Kieran Timberlake side, we definitely do, although the scope can be variable. You know, for instance, we might be doing a lease fit out for the OBO, Overseas Building Office of the government. In that case, you know, our LCA is going to be just looking at a lot of material, internal finishes options as for the materials, not looking at structure because that's set. So, we definitely do that. We also are starting to do more LCAs for hire on specific LCA challenges, optimizing a particular type of structure for a client. But we definitely do that in all of our projects. The scope's variable, the functional unit's variable as a result. But we definitely see it as an imperative. And also, we really work hard with Tally for all of our customers to make it as easy as possible to perform iterative LCAs. We have some mechanisms by which an LCA from one project, that data and definitions in Tally can be transferred over to subsequent ones. So part of our thinking at Tally is, okay, how easy can we make this so that it can be rolled into every project and not necessarily tacked on as an additional service because it's so easy to do.
Yeah, and I guess I wanted to share too, although we share these like larger case studies, a lot of what we're doing at Lake Flight 02 is really small things. So I've also had designers just come to me and say, hey, I know that, this is our best case scenario installation when it comes to performance, but what does that actually mean in terms of embodied carbon? And so I think that there's also a lot of ways you can use Tally to do really quick studies. And that's where I also see, really important kind of powerful design moves is it doesn't have to be, this like big long project, but you can just input here and there to help key design decisions.
And then the last question here is we have is about carbon offset tax credits, particularly for buildings and as a mechanism to encourage better embodied carbon performance. I haven't seen that in particular, but I have seen some places like Vancouver, for instance, is right now engaging in the development of baselines for projects in that city for developer projects. So when a new project goes up, it actually has to perform relative and certainly lower than a baseline building. And I think we're going to see something along those lines being evidenced in more areas. And the reason why I think that's probably where things are going to go is that's what's happening now for energy. You have a energy performance target that needs to be hit. And I imagine you'll see something similar for carbon simply because it folds into a familiar framework. But I am no prognosticator. I have not predicted anything accurately in 2020 so far as I can tell. So take that with a grain of salt. All right, well, I think that's it.
Is the end?
The end.
Thank you so much, Kate and Roderick, and thanks to everyone for joining us today. And thanks to our sponsors.
All right, take care, everyone.
See you at the
Thank you.
keynote.